K-12 Mindsetters, welcome to today's Physical Sciences show. Today we have a special revision lesson on rates and equilibrium. We have selected highlights from lessons shown earlier in the term to help you revise. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. You can also download the notes for today's show from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
So they tell you a catalyst speeds up the rate of a reaction. This behavior of a catalyst can be explained in terms of the activation energy and the collision theory, putting it into context for you. The first thing they tell you is the diagram below shows the Maxwell-Boltzmann distribution curve for a certain reaction. Guys, don't get too stressed about the Maxwell-Boltzmann part of this. That's named after the scientists who dealt with this, okay? That's the only reason why it's there. It doesn't mean anything, but it's named after people. So what this curve tells me, okay, is it's always going to have the shape that it's on here. It just either might go up higher or it might go out wider, okay? Your y-axis is what we call the number of particles. Sometimes it's called the fraction of particles, but pretty much this represents a number. So 10, 20, 15, 34,000, and of course we're not too concerned about that because we don't ever want exact values. So from this graph, you are not going to get asked to do any sort of calculations at all because you can't. All right, the maths is way too difficult and you don't do the right maths at school level anyway unless you do AP maths. So please don't stress about it. Along the bottom, along your x-axis, that's your energy of the particles. That represents the kinetic energy, so that's kilojoules. And what this graph does, this is not time, okay? So please, this is where it's different for you guys. We have to look at the graph in its entirety. The area under the graph, if I had to work out the area under the graph, that would give me the total number of particles in the system, okay? So the area represents the whole number of particles. Now, if we look at the graph over here, at this point here, that would be the maximum kinetic energy any particle has, okay? Well, sorry, not the maximum. That represents the highest fraction, I apologize, biggest number of particles. So this could be 20,000, 30,000, 40,000, whatever the case may be. That number of particles has whatever that energy is. And more than likely that you're starting to feel this temperature as the temperature, okay? As we come down here, the graph over here now gets lower and lower and lower because less and less particles have a high energy, okay? Lots and lots and lots of energy at this whatever this temperature is, okay? The activation energy is here. This is a set value. Now, the activation energy is 300 kilojoules, 400 kilojoules, 750, 10, depends on the reaction, okay? Any particle that goes to the right of this graph over here has enough energy. So that in this particular case, there's only a small number of particles that have enough energy for the reaction to take place. Anything to the left doesn't have enough energy, okay? Does not have enough energy. So a large portion doesn't have enough energy. This would probably be quite slow. We're going to come back to the graph in a second. So the first thing they say to you, explain in terms of the collision theory and activation energy how a catalyst influences the rate of the reaction. Well, I just said that to you. A catalyst lowers the activation energy, okay? So if we now look at the graph, and let's take away, I'll do another color. What that means is if I have to draw in where the new activation energy is and say it's over here, and this area under the graph has now got bigger, that means there are more particles with sufficient energy for the reaction to take place. Okay, so what does a catalyst do? It lowers, okay, I'm going to do this in point form for you. So it lowers the activation energy, which we will write as EA, okay, which means we increase the number of particles with sufficient energy, okay. And I'm using these terms very specifically, guys, the collision theory says they must collide in the correct orientation and they must collide with sufficient energy. So I've got to use those terms, okay? We're ignoring the correct orientation right now. So we're increasing the number of particles with sufficient energy, and that means that we will have a greater number of effective collisions, which means the rate will get faster. We have a greater number of effective collisions, okay? Now they say to you, redraw the above distribution curve and show the new activation energy when a catalyst is added to the reaction mixture on the diagram. I've actually done that already. In the actual exam question said, redraw it in your answer book. Guys, you must redraw it as it's given, within reason, okay? They're not going to go and measure and say, well, is the area the same? Guys, within reason. But what does that mean? This original activation energy must be shown. That's included in the original graph. If you don't show that original activation energy, how's your examiner going to know that you understand that the new one is to the left? You've got to have the original to show where the new one is. And then you would label this and you would say, so you would put it here and you would draw a line and you would say new activation energy with catalyst. Okay, label it. Give detail. Don't assume anything. Do not assume that your examiner is going to know what you mean, because they might not. Okay? So we've done that one. Oh, I love this question. Okay, it's one of those questions where you sort of can go, really? When milk is left at room temperature, it spoils rapidly. However, in a refrigerator, it stays fresh for a longer time. Use the collision theory to explain this observation. What are we saying? We've got room temperature, that's a temperature, and we've got a refrigerator. So we're going from a warmish environment to a cold environment. In a refrigerator, we are decreasing the temperature. By decreasing the temperature, we now have fewer particles with sufficient energy. Therefore, the number of effective collisions is smaller. Okay? In a refrigerator, we're lowering the temperature. Okay? That means there's fewer particles with sufficient energy because the kinetic energy of the system is getting smaller. Okay? Smaller number of effective collisions. Please remember, guys, that the definition of temperature is a measure of the average kinetic energy of the particles. Okay? It's a measure of the average kinetic energy of the particles. So whenever we talk about changing temperature, we're changing the kinetic energy. Increasing temperature increases kinetic energy. Decreasing temperature decreases kinetic energy. Okay? That's actually such a nice question because this was for about 7 or 8 marks. Nice one to do, okay? And they really are tending towards doing these. Question 2, and this is when I really hope you've managed to download the notes. It is long-winded, okay, but that's how your chemistry questions are going to be asked. Do not be put off by that, and read all the information because you're going to need it, okay? They tell you the active ingredient in a certain antacid tablet is the carbonate ion. This ion reacts with the hydrochloric acid in your stomach according to the following reaction. So we have the carbonate, CO3 2- plus HCl gives me Cl minus H2O plus CO2. Okay. The formation of the CO2 gas is an indication that the acid has been neutralized, and this brings relief from indigestion. You did learn in grade 10 that an acid plus a carbonate gives me a salt, water, and carbon dioxide. And in fact, the carbon dioxide is what makes you burp. Shh, don't tell anyone. After you've had the antacid, okay? And there are some people who think that the bigger the burp, the better the antacid tablet. Not necessarily. Okay, in fact, bicarb is a very good, it's an old no, it's a mother's home remedy type thing, but it works. It just tastes really bad. Okay, so a group of learners used 2 of these antacid tablets, so use the same ones, to investigate one of the factors that influence the reaction rate. They follow the method and use the apparatus given below. So we really want to find out what this one factor is. They say they place 1 antacid tablet in a conical flask, add 20 centimeters cubed of hydrochloric acid. Simultaneously, they stop the stopwatch, close the flask and the rubber stopper that is at the end of the delivery tube and attach it to the gas syringe. They measure the volume of the CO2 gas formed at intervals of 30 seconds, so they're measuring how the CO2, how the syringe increases, and then they repeat 1, 2, 3 above and grind the second antacid tablet to a fine powder. They're repeating all the steps. Temperature staying the same, concentration staying the same, they're changing surface area. Surface area. And you know what? Write a little note for yourself. I now know what they're looking at. So here's our diagram, okay? And what we have is we have our conical flask, the antacid tablet, delivery tube, stopwatch, retort stand, gas syringe. We're all happy. Okay, we've read through all the information. Let's go to the questions. First one, define the term reaction rate. Brilliant. We've now made a list of all our definitions in our studies, and we go, well, reaction rate is it's a measure of the change in the concentration of the reactants or products over time. Okay, so the reaction rate is a measure of the change in of concentration of reactants or products over time, or per unit time, over a period time, anything like that, perfect. Ooh, the questions we all like. Write down an investigative question for this investigation. Grade 12s, I'm guaranteeing you a question where you either have to write down an aim, a hypothesis, an investigative question, or a conclusion. They all 4 of those things have the same conditions. You must show the independent variable, the dependent variable, and the control. Okay? You must show the control. So dependent variable is the thing you're measuring. We're measuring rates of reaction. Independent variable is the thing we're changing, surface area. Control, we're keeping the concentration of the acid the same, the type of antacid tablet, temperature, all of those sort of things. So when I write this question down, it cannot be a yes-no question, which means you cannot start the question with does. Does the surface area affect the rate of the reaction provided all other conditions are kept constant? Yes. No, not the question. Okay. Is there a relationship between? Also can't be the question you asked, because the answer is a yes or a no question. You must start these questions with either what is, okay, or how does. So you're going to start the question with how does or what is. Your choice, okay? I would start with how does, and you would do something like, how does surface area, let's start it with an S, not a U, how does surface area affect the rates of reaction Okay, we've got our independent, dependent variables, okay, provided all other conditions remain the same. Now, the only reason why I'm saying that is because there's actually a lot of controls. So we've got to keep the volume of the HCl the same. We're keeping the concentration of the HCl the same. We're using the same antacid tablet. Sorry, we're using the same mass of antacid tablets. So there's a lot of controls in this one, which is why I'm saying that I provide all the other conditions stay the same, which of course you can't read, but let's just pretend. And in fact, let's just quickly write down those controls that I just said, because that's the next question. What are the variables that need to be controlled? Well, one is temperature, by the way. We really need to do this at the same temperature, so we're going to say temperature. the volume and concentration, we're going to do it this way, of the HCl. Okay, so it's going to be square brackets. The mass of the antacid. No, that's spelt wrong. Wow. Do you want to see that English isn't my strong suit? There we go. Antacid. Okay, those are the three most important ones. We are going to assume we're using the same one. Okay. Then, apart from the apparatus illustrated above, the learners need to use at least 2 other pieces of apparatus. So the question was, what 3 pieces of equipment would we need and why? Now, the first thing we'd probably need is something like a mortar and pestle, okay? Or, and if you didn't know what that means, something that you can grind the antacid tablet with. Okay, that's why you had to explain what it was used for, because in the question we go from it being in a solid to being in powder, so we need to be able to grind it. That's the first thing. The second thing we would need is a scale, because we need to keep the mass of the antacid tablet the same. Okay, so we need a scale to double check and to make sure. Okay, and the third thing we would need is a thermometer, because we want to make sure that the temperature remains constant. And by temperature remaining constant, I'm talking about the starting temperature. This is an exothermic reaction, which means the reaction is, as it takes place, will get hotter. But I don't care if the temperature changes during the reaction, it's the starting temperature that's important. Okay, then, what do they ask us after that? Then they say to you, the learners measure the volume of the CO2 gas formed in 30-second intervals in step 3. Write down the name of the apparatus that they used for measuring the volume. So we go back here and we go, well, where are they measuring the volume? This one's a bit of a giveaway because it's here with the gas syringe. Look back at the question, okay? They didn't ask you to make it up, but it's in the gas syringe. Now, for those of you who have never seen the gas syringe, which probably is a lot of you, in fact, even my school, and I'm actually at a very quite a good government school, we don't have one anymore because they break, unfortunately, and they're very expensive, the new ones. It's a syringe, like a normal syringe that you use injections for, but it's really, really big, and it's made out of glass, okay, and they're normally about that long, and it's made out of tempered glass to help. And what you do is you line the edge and you seal it, but you also make the inside, but you seal it with like Vaseline, which allows it to actually move the plunger part to actually move, okay? That new glass gas syringes are very expensive, which is why we won't ever replace them. We find other ways you can use. Instead of a gas syringe, another way they could ask you is we could actually turn a gas measuring cylinder, like the plastic one we use now, fill it with water, turn it upside down in a bowl of water and make the gas go underneath and up and push the water down. It's another way to do it, which is the way we would do it because we have that equipment and we can get plastic gas measuring cylinders, which of course are cheaper, last longer when they fall on the floor, which happens because accidents happen, they don't break, which is always a bonus. Okay, so then they say, consider the sketch graph below. Now, this is a rate graph, and what it does is it shows the rates of the reaction between the hydrochloric acid and the solid antacid tablets. Rate is 0 when we start because there was nothing there. We put the tablet in, and then the rate increases. This is a steep gradient. The steeper the gradient, the faster the reaction is happening. Starts to slow down, so the gradient gets less and less steep. Why? Because we're using up the reactants. The less reactants we have, the less collisions there are. The less collisions there are, the slower the reaction. Till eventually it goes flat. When it goes flat, the reaction has reached completion. Everything's being used up. No more reaction happening. Okay? They say to you, redraw the above sketch on the graph. You would draw it on your paper. I'm going to do it on here. On the same set of axes, sketch the curve Q that was obtained with powdered antacid. Now, we've just said, well, with the powdered antacid, powder increases surface area. Increasing surface area means there's more collisions available for bonding. The more collisions there are available for bonding, the more collisions will take place. That means there'll be more effective collisions. The reaction rate increases. So that means my reaction rate increases, but I use the same amount of everything else, eventually we'll go to the same place. It must finish in the same place. Guys, that is graph Q. You must label it, and you must have graph P on your original graph. Otherwise, there's nothing to compare it to. Make sure they are labeled. Very, very important. All right. The instruction on an antacid packet recommends that the tablets must be chewed for faster relief. How can chewing the tablets help? Okay, some don't even ask you to chew them, some you can dissolve in water. Or they come in powdered form already. I don't really like, and you drink. Why do you chew them? Because you're increasing the surface area. By chewing the tablet in your mouth, you're crushing it. By crushing it, you're increasing the surface area, and therefore it will react faster with the acid in your stomach. Okay, because you're increasing the surface area, which means there's more particles available for bonding. If there's more particles available, therefore there'll be more collisions. If there's more collisions, then more of the collisions will be effective, and it will work faster.
Okay guys, I hope you're enjoying this revision session. If you need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, but don't go away, we'll be right back. Welcome back guys, we have some great news to pass on to you. We will be bringing you winter school from the 30th of June till the 20th of July, starting at 10 a.m. every weekday. To get the full schedule, visit our website learn.mindset.co.za and look for the winter school link. Join us, it's going to be a lot of fun. But now it's time to get back to the lesson.
Now, what I've got, and this is nice, because this, probably most of you have never seen this question before. Yay! So it's not from an exam, it's only just come out. It's the exemplar paper for 2014. So this has come straight from the department, and I have adapted it because they had some other stuff in that we're not doing this week, so I've adapted it a little bit. But this is what you can expect at the end of the year. Okay, so this is the sort of thing you can do. And also in terms of study tips, the more past papers and exam type questions you can do, the better. That's how you get better at this, is by practice, 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 okay? And you'll see with all three questions we do today, they're all the same. They're all the same concept. So what do they tell you is a sample of N2O4 gas is sealed in a container, so we have a closed system, and is heated. Fine. The N2O4 gas decomposes to NO2 gas, and the reaction reaches equilibrium according to the balanced equation. So what we have is N2O4 gas. Remember, there's our nice equilibrium sign, means forwards and backwards, 2NO2, and delta H is greater than 0. Telling us delta H is greater than 0 tells me that the forward reaction is endothermic. That will be important when it comes to looking at conditions and how we can change equilibrium, but we're not going to do that today. The graph below shows how the concentrations of the two gases change as a result of changes made to the reaction conditions. Now, this looks different to a rate graph, so it's not exactly the same as the graph we did before the break. But what this is saying to me, okay, first of all, N2O4 are my reactants. So I always start with a lot of reactants. Always, always, always. NO2 is my product, and I always start with 0. In this first part of the graph, the reactants are being used up really quickly. Products are being made really quickly, till eventually we get to the stage where the graph is now parallel to the time axis. Over here, because it's now parallel, if I was watching this reaction, it would look as if no more N2O4 is being made and no more NO2 is being made. It will look as if the reaction has stopped. The concentrations are remaining constant. That means equilibrium is established. Then at T3, something happens, okay? We change a condition, temperature, concentration, pressure, whatever the case may be, and then a new equilibrium has to be established, and then we did that again at T4, okay? And then a new equilibrium has to be established. This, we're not worried about how we change the equilibrium for now. I just want you to see how the graph works. Then they say to you, define the term chemical equilibrium. Well, chemical equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. So that's what chemical equilibrium is. The rate of the forward reaction is equal to the rate of the reverse reaction. Nice and easy. Now they say to you, how does the rate of the forward reaction compare to that of the reverse reaction? So now they're asking you about rate at each of the following times, right? Only higher than, lower than, or equal to. And it's the forward reaction to compare to the reverse reaction. So what I'm asking is the forward reaction higher than the reverse reaction, lower, or equal to the rate? So the first one is at T3. Now, if we look at T3, at this point, I know we make a change, but I told you, because it's the part that I've circled, that up to T3, the graph was now parallel, the concentrations are remaining constant, which means that their rates are equal to. Okay, so the rates are equal to over here at T3. Actually, someone's screaming, I'm sure, right now, going, Tracy, you lie, you lie, you lie. And they would be correct. I do lie. I don't lie, I'm just not telling you the truth.
You're just parallel to the truth.
Yeah. Anyway, moving on. Let's correct what I just said to you, shall we? Okay. Guys, leading up to T3, they're equal to. So actually at T2, it's equal to. At T3, I now change something about the reaction. And can you see what happens? Let me just take this out so you can see. At T3, over here, can you see that there's a spike in this forward reaction? Well, there's a spike in making N2O4 and a decrease in the NO2. What that tells me is that I've done something to cause the NO2 to be used up and to make more N2O4. If I'm using up the NO2, then that means the reverse reaction is being favored, because when I use up the NO2, I'm making N2O4. Okay? So actually, I've got this the wrong way around. I do apologize. It's higher than, it's greater than, it's faster. Okay? At T2, they're equal to. Because T2, if you look really closely at the graph, T2s actually starts after they become parallel. Okay? After they go parallel to the graph. Between T1 and T2, it actually starts to reach parallel. So at T2, they are equal to each other. But then we get to the fun question. And right now, my learners are all cringing because they know that means I like it, and that means it's probably a little more difficult than you're used to. Okay? They don't believe me when I tell them anything's fun
Just
anymore.
a little bit.
They don't.
A little bit difficult.
No, but then this is what makes it fun. Anyway, so they tell me that initially, so we're going to look at some important, initially, 0.2 moles of N2O4 gas is sealed in a 2 decimeter cubed container, so that's important, and heated to 100 degrees, so that might be important as well. At equilibrium, it's found that 0.19 moles of the NO2 gas has decomposed to form NO2. So in other words, the N2O4 has decreased its number of moles by 0.19 moles, okay? Calculate the Kc constant for this expression. Now some of you are going, not a chance, Tracy. Far too little information, not at all. We are now going to do what is known as a rice table. Some of you might learn this as an ice table, okay? I add in an extra line, and a lot of teachers do, but it's not necessary for the marks. It's just to help you. First thing we need to know is that the rows on this table are the same regardless of the reaction, okay? So that's where we're going to start. So we're going to start with our table, and we're going to go fine. I'm going to need a heading row over here. I'll tell you how many columns in a second. Okay. Well, the number of columns is actually easy. We need one column to write in everything of what we're going to calculate. And then the number of next columns depends on the number of things in your reaction that are gases and solutions. So we only have two N2O4 and NO2. So I know that all I need is 2 more columns other than my original, and then I'm going to add in a line which my learners have last year they named the fearless line. they decided something had to be named after me, because it's just something, it's not in any of the textbooks. It's just something I do to remind us where the products and reactants start, okay? Because sometimes we forget. So I put in a double line over here. That's just something I do. You don't have to, all right? A lot of you teachers won't. It's just when you put a double line in there, then you know where your reactants and products end, and it's important for a little bit later on. So we have N2O4, so we're going to put that over there, and we have NO2. And all I'm doing right now is I'm setting up what I need to answer the question. In my first line, I have to have the molar ratio, which is where the R comes from. And this is the, sorry, I didn't want to write that in. The ratio part is from the numbers in front of your balanced equation, okay? So the balanced equation was N2O4 goes to 2NO2, okay? I'm still not going to go all the way up again, so it looked like that. So N2O4 is 1, NO2 is 2, okay? It comes important later. Your next line is always your initial number of moles. Some of your teachers may have taught you to use concentration. That's fine. It's just sometimes concentration gets a little difficult conceptually when I start adding and minusing things, okay? I'll put some information in there in a second. My next line is called the change line, which will also be in number of moles. Okay, can you see where the word rice is coming from? RIC, which then hopefully some of you go, well, that means the last letter has to be an E, and it is, and it's equilibrium. So now here I want to know what my equilibrium, and in this case it's equilibrium number of moles. Okay, but KC calculations can only be done if you have an equilibrium concentration. So that means I have to add in one more row, okay, over here, and this last row is my equilibrium concentration, okay? Because it's concentration, this is going to be in moles per decimeter cubed. All right, these lines, so it's RIC table, okay? Doesn't matter. Those lines are the same, regardless of what happens with the rest of your table. Your next step is to go to the information given and write in everything you've been told. So first of all, we started with 0.2 moles, 0.92 moles of N2O4. Brilliant. They told you at equilibrium, it was found that 0.19 moles of the gas is decomposed. So the change in N2O4 was 0.19. Okay, and that's all they told you, happens at 100 degrees, and for equilibrium, I need to know that the volume is 2 decimeters cubed. And I'm sure some of you are going, yeah, right, Josie, like I can get to equilibrium from here. Of course you can. Watch. First and foremost, we always start with zero product. Always, always, always. So that's the first thing I know. Second of all, and this is why I do the double line, we always minus from reactants and add to products. So I had 0.92. They told me I used 0.19, which means 0.92 minus 1.9 gives me 0.919 gives me 0.73. Okay? We all followed me so far, which actually means I can work out the concentration of this one, and I have actually done some of the calculations just to make it a little bit easier. I'm not going to show them all to you. Remember, concentration is number of moles over volume, so that means I'm going to have to go 0.73 divided by 2, which you can write into this block if it's going to make it easier for you, and that means this is 0.37. First line's easy. I'm pretty sure most of you okay with that. But now you're going, hang on, wait. Okay, I get, you can probably also say to me, I get why we end up with what we get for N2O4, but now what do we do with the NO2? Because I really have nothing. This is where things get exciting. Now you have to use the mole ratio. This you need to get. this line and that line must have the same ratio. So it's a 1:2 ratio, which means when I look at these numbers, it must also be 1:2. Okay? And a little trick, it's what I tell my learners, it's what we call timesing by 1/got. I take what I have, the 0.9, and I times it by the mole ratio of the substance I want, and divide it by the mole ratio of the thing I have. So watch what happens, and I do this in pencil, is you go, I'm going to take the 0.9, and I'm going to multiply by 2. Now use your imagination. Can you see when it crosses the line that looks like a multiplication sign? Let's go with it. And then I'm going to divide by 1. That's almost like a division sign. So I'm going to multiply by 2, divide by 1, which means this becomes 0.38. Okay, it's a 2:1 ratio. You can go check that. I always make reactants double line. I started with nothing. I'm going to add 0.38, so this was a bit of a trick question. That gives me 0.38. This equilibrium line does not have to be the same ratio as my top one. It's ratio and change. Those must be in the same ratio. Okay, always, always, always. Then I'm going to take the 0.38 because I need the volume. I'm going to divide by 2. So that gives me 0.19. We've actually done the hard work. Now some of you are going, oh, don't worry, we'll do another one. Okay. From here, now I need to write my Kc expression. Now my Kc expression is the concentration of the products divided by the concentration of the reactants. My products was the NO2, but there's a 2 in front of the NO2 in the equation, so it's squared, divided by the concentration of the N2O4. I found out that the NO2 has a concentration of 0.19. The concentration of the N2O4 was 0.37. And that's 0.19 squared, don't forget the square. We put that into our calculators and we get, now I've put it into scientific notation just because it's quite a small number, it makes it more accurate. If we do it on our calculator, so we can see over here, let's just put this over here. So we go 0.19 squared divided by 0.37 equals, take it out of that. It's actually 0.09756. Now the reason why I'm putting it into scientific notation, it gives me a more accurate answer, because if I had to round that off, and remember it's always to 2 decimal places, round it off, this would actually give me 0.1. Oh, see, I'm used to using the things on my, trying to do like I do on my whiteboard. It would actually end up as 0.1. Can you see? That's not as accurate at all, because we'd have to round off from the 7. So rather do it into scientific notation when it looks like that. It's one of those things that's not that important, but they really want 2 decimal places. Okay, to 2 decimal places and as accurate as possible.
I think it's time for a break now. Don't go away. We'll be right back. Welcome back from the break. Let's not waste any time and get straight back to today's revision lesson. Over to you.
Let's get on and have a look at some questions. We're going to do questions on chemical equilibrium, applying the Chatelier's principle. Okay, so let's look at the first question. Here we go. Question number 1, and it says the following things. Let's pick out the key information. And the first thing was we're told hydrogen and oxygen are enclosed together in a 200 centimeter cube container at a temperature of 118 degrees Celsius. So I hope you can see the reactants are hydrogen and oxygen. A closed container means that after some time at this temperature, remember chemical equilibrium is specific for a temperature. And that's why it's related to temperature, and only temperature will change the Kc value. we're told the following, over a course of periods of time, the chemical equilibrium occurs in the container. So we've got hydrogen, a ratio of 2 lots of hydrogen, 2 moles of hydrogen, reacts with 1 mole of oxygen to produce 2 moles of water. Now notice, they're all gases. So when we're doing chemical equilibrium, it's very important that we understand that. If there was a solid or a pure liquid, we would ignore it in the Kc calculation. We'd ignore it as we're considering our reaction. We're also told here that delta H is negative. This means that it is exothermic. Okay, means it's giving off heat, and we'll need to use that in our calculation now. So let's go to the next part. It says in the table below, possible changes to the equilibrium conditions are proposed, as well as those aspects on which the changes can have an effect. Write down no effect, increase, decreases. So guys, it's important when you're reading your June exam paper. If they give you a question like this, don't give them an essay. Teacher wants to know increase, decrease, no effect. Give it to them like that. Let's have a look and let's analyze based on those 5 or 6 principles that we spoke about, the template for answering these questions. I'm going to show to you how we set it up. Might take a bit longer for the first couple, but we're going to have a look at them as we go through them. So see what it says. The first change that we're going to look at is pressure in the container decreases at constant temperature. So we don't have to worry about 2 things. They always have to say if pressure changes, it's at constant temperature. So now, let's have a look at the equation. A change in pressure will affect the volume, usually. Okay? It usually affects the volume. And the way that we do these is we look at the balanced equation. And we say, how many moles have I got on this side? How many molar volumes have I got over there? And I hope you can see you've got 3. You've got 2 hydrogens and 1 oxygen. And on this side, we've only got 2 of the water vapor. So we've got 3 volumes on the left-hand side, 2 volumes on the right-hand side. We're going to decrease the pressure. Now, a decrease in pressure will mean that you are going to have an increase in volume. Let's say that again. Remember, pressure is directly proportional to volume. That means if you decrease this one, you will increase the volume. As the one goes up, the other goes down. So the volume here increases. So if we decrease the pressure, we're all happy and stable. Which side of the reaction occupies the bigger volume? Which one's got more, needs more space to occupy? Well, I guess you recognize that it's uncomfortable, Abram, for 3 people to fit onto a motorbike.
Yeah.
2 people would be fine. Can you see that's decreasing the space? Now we're increasing the space. Now we're going from a motorbike to a motorbike with a sidecar. So which one are we going to go to? It's immediately going to change to accommodate the 3 people. So what effect does this have, decreasing the pressure on the quantity of oxygen? So if we decrease pressure, listen to it. First of all, the disturbance is decrease the pressure. That means we've increased the volume. What's going to happen? We must take up that additional volume. We must favor the side that increases the molar volumes, because we've got more space to fill. We want to fill that space. So the counter reaction is to identify now which reaction is favored. We've said pressure is related to volume. We want to see the change in volume. We want to fill up the volume. So what's that going to mean? The back reaction is favored. That one is favored. If that reaction is favored, what does that mean? It means that we're going to get more of that. Yes, we will get more of this as well. The back reaction, remember, takes water and produces oxygen and hydrogen. We only were asked about what's the effect on oxygen. So I can confidently say that if we decrease the pressure, we're going to need to increase the volume. We're going to favor the reverse reaction. We're going to increase the concentration, or not the concentration, but the quantity here. It's in a concentration, it's a fixed volume. If that was, we can't talk about fixed volume because we are changing the volume. What's the effect on Kc? There's no effect. None. No change. So we should really say no effect. No effect. So this one increases. What's the effect on the value of the delta H? Guys, there's no change here. Delta H stays the same. Even if you add a catalyst, okay, the delta H is not going to change. So there's no effect. There's no change. It has no effect. Let's go to the next one. And I hope you can see this is how we apply Le Chatelier's principle. So the next question, or the next part says, for us, water vapor is removed from the container. So what's the stress? We're taking away something. What are we taking away? One of the products, water vapor. So let's go to the equation and let's work this one through. I'm going to just undo all of that writing so that we can have a careful look at it. We say we're going to take away some of this stuff here. We're going to subtract water vapor. So if we take away, what does the system want to do? It wants to replace the water vapor. So we take some away, it replaces it. Okay? So which reaction is the one that makes water vapor? H2O gas. Well, I hope you can see it's that one, the one pointing to this. So we wanted to take this down. The reaction system says, no, I must replace it. I must push it back. Now, if I'm going to push the forward reaction, favor the forward reaction, that means, guys, that this has to be used up and that has to be used up. So, go back to the table now and let's see exactly what's happening. So for the water vapor, if I remove water vapor, what's the effect on oxygen? Well, it's going to decrease. If I take away some oxygen, then it decreases. What's the effect on the Kc? Remember, this is just changing concentration, changing the amount. So there's no effect. And on delta H, no effect. I'm just going to put double dots there. Right. Now the next one. Change in temperature. Guys, you've got to watch this very carefully. Temperature changes to 105. Now, let's get the original temperature. It was at 118. Was at 118. Be very, very careful when you're dealing with temperature. It's gone from 118 to 105. So what we're going to identify, first of all, there's a decrease in temperature. Okay, so there's a decrease in temperature. What we need to recognize, if the temperature goes down, then what's the system going to do? It's going to want to increase the temperature. That means it wants to change and increase the rate of the exothermic reaction. How did I get that? Well, remember, exothermic reaction actually produces heat. If I decrease temperature, the system tries to warm it up. If the outside temperature gets cold, what does your body do? It wants to shiver. And what's it doing? It's increasing the temperature. Same thing happens here. So it increases the rate of the exothermic reaction. And if it increases the rate of the exothermic reaction, now we have to say what reaction is favored. Let's go to our reaction again, and let's have a look at what information we need to understand here for this part of the reaction. Every time, go back to the equation. So, what is this telling us? We're dealing with temperature. When you're dealing with temperature, you must look at delta H. Delta H is negative. That tells me that it's producing heat. I can, in my rough notes, say heat is a product. It's being produced. If I'm taking away heat, I'm decreasing the temperature. Think about it, removing this. Then you can think about it removing the product. What's the system going to do? You tell me. The system will try and replace heat. Yes, it favors the exothermic reaction. If it favors the exothermic reaction, what's going to happen to the oxygen? It's going to go down. What's going to happen to the hydrogen? It's going to go down. So, in exactly the same way, a decrease in temperature will favor the forward reaction. So it favor the forward reaction. Okay? And if it favors the forward reaction, we can say the oxygen concentration decreases. Now, guys, the next one, the effect on Kc and the effect on delta H. This one is no effect. But I want to look very carefully at the next one, because I want to look at what the Kc is. The Kc is, for this reaction, H2O squared. Remember, it's O2 and H2. Now get the balancing coefficients in. I'm just reading it off so you can see. There's a 2 in front of the H, there's a 2 in front of the H2O, there's a 1 in front of the O, so I can put a square on there. So now have a look at this reaction very carefully, or this expression, Kc expression. Remember what we've said. We've said that, first of all, this is going to increase, but these two are going to decrease. Guys, this is a denominator. Denominator. This is the numerator. If the bottom number gets smaller for any fraction and the top number gets bigger, so if we start with 1 over 10, and let's change it and make the bottom number smaller and make the top number bigger, and let's change it and do it as a practical. So we're going to make this 2 and make this 5. Let's make this, the next one, 4, and let's make that 2. Let's make this one 8, and let's make that 1. Can you see what happened? It was small over here. 1/10 is 0,1. What's 8 over 1? It's 8. It's got bigger. So if we make the number at the bottom smaller, and that's what we've done, and make the top number bigger, we're going to get a bigger number. So what's happening to the Kc? The Kc value increases. Kc increases. Let me fill that in my table so we've got it clear. So this one increases. Very, very important. Last thing, a catalyst is added. Oh, guys, you've got to be very careful with a catalyst and make sure that you understand it. So what a catalyst does is it speeds up both reactions. So if the first one, the forward reaction goes faster and the reverse reaction goes faster, there's no effect on the concentration. There's no effect on the Kc, and there's no effect on the delta H value.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get the notes and to watch the videos from the term. Goodbye.